Hello everyone and welcome to the next episode of the Extreme and Probabilistic webinar. Today our speaker is Torsten Mütze, partially from University of Warwick and partially from Charles University, two places where I studied. So but at both times Torsten was studying at ETH where I went after my studies. So we really seem to be reversing our steps in a bit. Anyways, so yeah, he will be talking about combinatorial generation via permutation languages. And maybe before I pass the virtual token to Torsten, just a couple of general remarks. If you are regular to the seminar, you know them by heart even better than me. So firstly, this talk is being recorded. So in case you maybe want to ask a question, but you don't want to have it on a record, then wait till the end of the talk. We will have a recorded section of questions, and then we will stop the recording and have maybe more open and completely unrecorded part for another chat. Also, if you will have questions during the talk, feel free to unmute yourself and interrupt Torsten, or if you don't want to do that for one reason or another, just type your question in the chat, and either it can happen that somebody else from the audience will promptly respond, or if not, we will forward the question to Torsten. All right, so I guess with this, I hope I haven't forgotten anything important. Anyways, if yes, then we will see. Okay, that's all from me. And now, Torsten, the virtual stage is yours.
Yes, thank you very much, Hansa, for the introduction and the nice words that you mentioned. It's very nice to speak here, and thanks for the invitation. What I present is joint work with several people, Jean Cardinal included, Liz Hartung, Hoang from Zurich, Arturo Merino, he's my student in Berlin, and Aaron Williams. And it's also a mix from several results, some of them that have already been published and some that are still in the pipeline, so to say. So it's ongoing and past work at the same time. To start with, in computer science and mathematics, we frequently encounter different kinds of combinatorial objects. So here are some examples. Imagine, for instance, the set of binary trees with a certain number of nodes, or let's think, for instance, about the set of permutations of some ground set, or another class of objects could be all the bit strings of a certain length, or with some properties, or maybe all the partitions of some ground set. So you can choose your favorite class of objects to think here. And there's a number of fundamental algorithmic tasks that we want to perform with these objects. Yeah? So one thing, of course, is we want to count them. We want to know how many there are. Another important task is we want to sample uniformly at random one of the objects, or another task is we want to find the best object according to some objective function. And there's another important task, and this is what we will focus on here, and this is exhaustive generation. So we want to have an algorithm that generates all the objects in the class, each object exactly once. And this is covered in depth in this Knuth's volume 4A of the Art of Computer Programming is devoted to this task. And the goal, of course, is to come up with an algorithm that lists all these objects as efficient as possible. And ultimately, we will aim for an algorithm that generates each new object in constant time. This is somehow the ultimate goal always. And of course, if we aim for such an algorithm, then it entails that when we go from one object to the next, we can only change it a little bit because we have only constant amount of time. And such a listing where objects are listed in minimum change order, this is often referred to as a gray code. So here are some classical examples of such gray codes. So for instance, it's known that you can list all the binary trees, and in each step you just do a tree rotation when going from one tree to the next on a certain number of nodes. So something else very classical is the Steinhaus-Johnson-Trotter algorithm. It lists all permutations of some length, and in each step it only does adjacent transpositions. So you just swap some two neighboring symbols in the permutation. Another thing is the binary reflected gray code. So you list all bit strings of a certain length, and in each step you just flip a single bit. And the last example is the gray code U2K for set partitions, where in each step you just remove one element from a set and you include it into another one of the partition. And this task of exhaustive combinatorial generation is closely related to or gives rise to a family of graphs that are known as flip graphs. So a flip graph is defined as follows. You take as vertices the combinatorial objects that you want to generate, and you take as edges those pairs of vertices that differ in a small change. So the edges of this graph, they capture the change operations. So this is, for instance, the flip graph that you get if you take binary trees and any two that define a tree rotation, they are connected. And then you get this graph. Or this here is the flip graph of permutations under adjacent transpositions. And this is the flip graph of binary strings under flipping a single bit. And yeah, in this way you get a huge family of flip graphs depending on the objects and depending on the change operation. And it turns out that many of these flip graphs that you get, they have a lot of structure. In particular, they can often be equipped with some poset structure or even realized as polytopes. So for instance, this flip graph on binary trees, it can be realized as the lattice, and this is this classical Tamari lattice, and the corresponding polytope is the associahedron. The permutations, they can be ordered, and the corresponding poset is the weak order, and the polytope is the permutahedron. And of course, the example on the right-hand side, this is the famous hypercube, and this arises as the Boolean lattice, yeah, subset inclusion lattice. So, and this task of exhaustive generation now, of course, corresponds to finding a Hamilton path or cycle in these flip graphs. So here's a Hamilton cycle in each of these three particular flip graphs. And moreover, many of these flip graphs that you get, they are highly symmetric. So in the sense that they have a high degree of symmetry. For instance, the permutahedron and the hypercube, they are vertex transitive graphs. And the associahedron, for instance, is a regular graph. And there is a very famous conjecture due to Lovers from the 70s, which says that every vertex transitive graph has a Hamilton path. So this connects this exhaustive generation problem with this famous Lovers conjecture. If you look at the area of exhaustive generation, then you will find that many of these papers, they produce some tailor-made algorithms to solve this generation task for one particular class of objects. And there's few general frameworks available. A few exceptions are listed here. This is in contrast to these other two tasks that I mentioned in the beginning. So for instance, if you want to do counting, then there's this very powerful framework of generating functions that you can use. Or if you want to do random sampling, then there's this very general tool set of Markov chains that allow you to do this. And for generation, this is somehow missing. And this work is somewhat a step in this direction, a general framework to solve this exhaustive generation problem for a rather large class and range of combinatorial objects. In particular, as a result from our framework, we will get all these aforementioned algorithms, so these four classical gray codes, they will be special cases of our framework. And moreover, we will obtain many new results and algorithms for various other combinatorial objects, and also on the corresponding lattices and polytopes. So these gray codes are in a certain sense optimal because they correspond to walks on these lattices and polytopes. And the basic idea of the framework is, of course, to encode the objects in some way. Yeah? So every object is encoded as a set of permutations. So Sn denotes the set of permutations of length n, and Fn is a subset. These are the permutations that we will use to encode the objects. Of course, I will tell in detail more later how this works. And now we agreed somehow that permutations are the things that we will generate, and they will encode the objects. We have to discuss what is the minimum change operation to go from one permutation to the next, and this operation is what we call a jump. So a jump in a permutation means you take an entry and you move it across some neighboring entries that must be smaller. For this instance, in this example here, the 5 jumps over the 1, 3, and 2, and what you get is this. So technically, it's a cyclic rotation of this substring by one position, where the numbers that you jump across, they must be smaller than yourself. So the 5 can jump across 1, 3, and 2, for instance. There will be some more examples here. So you can imagine that these numbers are somehow dolls that correspond to the height of these dolls. And then this means a doll can jump over some neighboring dolls, but the neighboring dolls, they must be smaller. Otherwise, it cannot jump over those. So for instance, this doll can jump by 3 steps to the right. It could also, so this would be a right jump. It could also jump only 2 steps or only 1 step. It could also jump to the left by 1 position, but it could not jump all the way to the right because there's this larger doll in the way. Yeah, so this is a jump. Okay, and here is our basic algorithm that we propose to generate a set of permutations exhaustively. So this is a greedy algorithm, and it works as follows. So you start with an initial permutation from this set Fn. So Fn is the set we want to visit. We want to generate, and we start with one of those permutations. This will be described later, what exactly we have to choose as the initial permutation. And then once we have a current permutation, we repeatedly apply the following greedy rule. We look at the current permutation, and we try to do a jump with the largest possible value. And this jump should be minimal with respect to this set Fn. I will say in a moment what this means. And we choose this value that jumps the largest possible in order to create a previously unvisited permutation. So we keep visiting new permutations as long as we can, according to this greedy rule. And minimal jumps means that if I decide to do a certain jump, then it must be a shortest possible jump. So no shorter jump of the same value produces a permutation in Fn. So for instance, if I decide to do this jump here, then this would be a minimal jump if this jump is not possible. So this jump would lead me out of this set Fn. Yeah, then this jump would be minimal. This has to be outside of Fn. This one, this one, this one, this one. So they all have to be permutations that are not in Fn. Then this jump is minimal. And only such jumps I do. I only do minimal jumps, and I do them with the largest possible value. This is the whole algorithm. And the algorithm can, of course, go wrong in the sense. So what can go wrong? It can go wrong that maybe no jump is possible. Yeah, you have maybe you try all the possible values that can jump, but no jump leads to anything new, and then you stop. And similarly, it can happen that a value can jump left and it can jump right, and then the algorithm doesn't tell you what to do. So the direction is ambiguous, and then you also stop. So there's 2 stopping criteria. You keep going with this greedy rule, and there's 2 ways that you may get stuck. And when you get stuck, you just stop. So here's an example. Suppose you want to generate these 5 permutations, this set of 5 permutations of length 4. And let's say we start with this permutation. Was there a question?
Yes. So could you go 1 slide back?
Yes.
And so you described why you can't. So why didn't you try going to the left with 6? So moving 7 to the 6, because that wouldn't be minimal, or
this could also be a minimal jump. Yeah, every value has at most 1 minimal right jump and at most 1 minimal left jump. And if in the algorithm, if it ever happens that the largest thing could jump left and right, then the direction is ambiguous, and then you stop, because then you don't know whether you should go left or right first. So ideally, it's always you can only jump in one direction, and then you jump only the smallest possible distance in that direction.
Okay, thanks.
Okay. Yeah, very good question. So suppose
question.
Yes.
Is there a reason to stop the algorithm when it's ambiguous instead of taking a random direction?
Right. This could be one somehow idea to improve the algorithm. but somehow we haven't found any instances where somehow this improved version would allow you to do more than somehow this. Of course, you can make an artificial example where somehow this improved algorithm generates something that our algorithm does not, but there's no example from the real world that we saw yet where somehow changing the rules would somehow make it much more powerful somehow. Yeah, but it's a good
Okay.
idea. Or some kind of, it doesn't even need to be random. Yeah, you could introduce some tie-breaking rule that says, I don't know, always jump left if you don't know what to do or something like that. Yeah. But so far we haven't seen any example where this would like improve it for a really interesting example.
Okay.
These are good suggestions. Okay, so here, let's say we start with this one and we try the largest possible value. It cannot jump to the right because this permutation that I would get is not in the set. And it can jump left by one position. So this is what I do. I get this one. Now again, I try jumping the largest one to the right. It cannot jump, yeah, because one of them is not there and the other one I have already seen. But it can jump to the left by one position. This is what I do. So I get here. Now the 4 cannot jump. Okay, you can check this. The 3 cannot jump and the 2 can jump. So you jump the 2 and you get this. And now the 4 can jump all the way to the right. And then you have seen everything. And now you have a successful run of the algorithm. Let's look at this case. We start with another one, this other permutation from our set. The 4 can jump all the way to the right. This is a minimal jump. We do it. And now we get stuck. From here, we have no other jump that we could do. So we are in one of these failing cases. And to also show the last case, suppose we start with this one here. The 4 can jump left one or right one. You don't know what to do, so it's ambiguous, and then you stop immediately. So these last two cases, the algorithm went wrong. And now, of course, we want to understand when is the algorithm successful. So we say that if this algorithm generates the whole set, then we say, no, if everything is visited, we say that it generates the set. Observe that by definition of the algorithm, we will never visit anything twice, yeah, because by the rule, by the greedy rule, we only go to new stuff. So we never visit anything twice. And the question is now, when does the algorithm generate the set? So when is it successful? And for this, we look at the so-called tree of permutations. So this is an infinite rooted tree. The root is the.
Sorry, Torsten.
Yes, yes.
I have a question. If you can go one slide back.
Yes.
So you are saying, okay, so in the algorithm you may have choices, but
yes,
go only so that you create something new. But
well, in the algorithm you shouldn't have choices, right? There's never a choice.
No,
like
but so that okay. So but now I'm confused with this. So that a previously unvisited permutation is created.
By this you mean previously in the list, like you have seen already 10 permutations. So when deciding what to jump, you look always at the previous 10.
That's so. Yes, I understand. But then isn't the whole point of this algorithm, or shouldn't the whole point be that the algorithm is fast?
Yeah. Now you're talking about efficiency. This is an important issue. I will come back to this. Yes, a very good question. This algorithm that I state here is not at all efficient. Okay. But I will talk about how to make it efficient in a moment. Yes, okay. That's a very good question. This algorithm is very bad because it always has this exponentially long list and keeps looking into this very long list. Yeah, that's a very bad algorithm. I agree. Yes, that's just the conceptually what the algorithm does. If you want to implement it, you have to do something else. Yeah, I will come to this. Very good.
Okay, thanks.
Good question. Okay, so let's first talk trying to understand the conditions under which the algorithm works. Let me just, no, that's fine. So for this, we look at this tree of permutations. So it's an infinite rooted tree. The root of the tree is the empty string or empty permutation, and the children of a permutation you get by inserting the new largest symbol in all possible positions. So you have a permutation of length n, and then you put n+1 in all possible gaps. These are the children of your node. And this gives an infinite tree, and on depth n, you have all permutations of length n. Every permutation appears exactly once. And now we, let me just disable the phone. And now we want to color the nodes of this tree. So we want to give each permutation a color. And the red permutations, the red nodes, these are the ones where the largest symbol is at the leftmost or rightmost position. So these are those permutations. And on the other hand, the green nodes, these are the ones where the largest symbol is not at the boundary, so somewhere in the middle. And now I allow you to prune subtrees from this infinite tree. And the ones that you may prune are the green ones. So green says you can prune it, and red says you cannot prune this subtree. So for instance, I may decide to prune this subtree, and I may decide to prune this one, and maybe also this one, but I may never prune the red ones. I may never prune a subtree that has a red node as its root. And this pruning, of course, can be done in several ways. And if you look at the permutations on some level that survive the pruning, then you get a subset of all permutations of length n. And such a subset we call a zigzag language. So any such subset that you get from after doing the pruning, this is what we call a zigzag language. So for instance, originally this level had 6 permutations. Now one of them is pruned. So the remaining 5, they form a zigzag language. And originally this level here had 24 permutations, and now I pruned how many? 4, 5, 6, 7 of them. And the remaining ones, they form a zigzag language. So here are 2 examples. For instance, if you prune nothing, then what you get are exactly all the permutations. And on the other extreme, you could prune all the green nodes. And then what would you get? You would get all permutations without peaks. So a peak in a permutation is a triple where the biggest value is in the middle. And permutations without peaks, they look like a valley, basically. So these are the ones at the red nodes, because these are the ones where the biggest symbols are always at the boundary. So these are the ones that you get if you prune everything. So these are the 2 extreme things, but you can do anything in between. And the main theorem of our work is that this algorithm J succeeds to generate Fn if it is a zigzag language. So for any zigzag language, the algorithm will be successful if you initialize it with the identity permutation. So this is the one that you should start with. So this is a sufficient condition. Yeah? If it's a zigzag language, then it works. It's not an if and only if, but it's a sufficient condition. And you can prove it by induction over this tree, but I will not do it here. And what is nice about this, that it's a rather powerful theorem, because the number of different zigzag languages is enormous. Yeah, it's double exponential in n, because of all the different ways that you can do the pruning. Yeah, for every green node, you can either say I keep it or I prune it, and this is like a huge number of choices. And this is why you have many different zigzag languages. And not only that, many of them are really interesting combinatorial objects. So they are not just artificial languages, but really useful ones. Many of those encode interesting objects, as we will see in the following. So here are 2 examples. If we start, again, these 2 examples, the 2 extreme ones. On the left, we will want to do all permutations. On the right, we will want to do the permutations without peaks. These are zigzag languages. For instance, if you run the algorithm with all permutations, the first one is the identity. And now you see why we call it a zigzag language, because this biggest symbol, the 4, jumps most of the time and goes back and forth in this zigzag way. And in fact, this ordering of permutations that you get here from this algorithm J is exactly the one that you get from the Steinhaus-Johnson-Trotter algorithm. So the minimal jumps in our algorithm, they become adjacent transpositions. So in this case, a jump will always just jump over one adjacent entry, and this will just be an adjacent transposition. And this is exactly the Steinhaus-Johnson, gives exactly the Steinhaus-Johnson-Trotter algorithm. Now let's look at the permutations without peaks. Again, we start with the identity, and then we let the algorithm run. And again, that the 4, always the largest value, does this zigzag pattern. Then the first thing we may wonder, if we generate a subset, do we also get a sublist? And the answer is no. So if we generate a subset, we don't get necessarily get a sublist. So the order may get messed up, as you see here. Now that we see that the number of those permutations without peaks is 2 to the n-1, we may wonder there should be some kind of bijection of these peak-free permutations to binary strings of length n-1, because there's also 2 to the n-1 of those. And this mapping I want to describe now. So you can get such a binary string of length n-1, and you number the bits from 2 up to n-1, and you set the ith bit to 0 if in the permutation the value I is to the right of all the smaller entries, and you set it to 1 if it's to the left of the smaller entries. So for instance, if you only look at where is the biggest symbol, where is the 4, then it starts on the right, so you have a 0 bit, then it jumps on the left, so it's a 1 bit, and then again it jumps later to the right, so you get a 0 bit. Yeah, so this is the bits that you get for the 4, and in the same way you get also bits for 2 and 3. And now you get a ordering of binary strings, and somewhat surprisingly, the ordering of binary strings is the binary reflected gray code. And the minimal jumps in the permutations, they correspond to flipping a single bit in each step. So you get an ordering of binary strings under bit flips. So based on these examples, I want to describe on this slide on a very high level the general approach. So the general approach of this framework would be you start with your favorite class of objects that you want to generate. First thing you need to do is you need to encode them somehow as permutations. So you need to come up with some natural mapping F that rewrites these objects as permutations. Then hopefully this set of permutations is a zigzag language. Only then somehow you can use our theorem. If it's a zigzag language, then you run the algorithm J. It produces some listing of the objects. Now you translate back this listing to your objects. Yeah, by applying F inverse. What you can also do, and this is even more interesting, you can directly translate the algorithm J and look at it. What does it mean in terms of your objects? So you get a greedy algorithm for your objects obtained by translating algorithm J. So I will tell you an example how this works in a moment. And of course, then you also need to understand how do the minimal jumps on the permutation translate into the changes on your objects, and very often indeed we get these minimal change guarantees. In fact, even works on some kind of lattices and polytopes. So this is a guarantee that somehow we get a nice ordering of the objects, one that gives fast algorithms. Okay, so let me show you this translation of the algorithm here for this example with the peak-free permutations. I already told you this bijection, and now let's translate the algorithm. So algorithm J on the permutation set start with the identity permutation. This translates into a start with the all zero string. And then the algorithm J set do a jump with a minimal jump with the largest possible value. This translates into flip the rightmost possible bit. That creates a new string. So this is a greedy description of the binary reflected gray code that you get in this way. And a similar thing you can do in each case. So for each application of this framework, you can translate the algorithm and rephrase it in your on your objects, so to say. We will see more examples in a moment. And now let me come to this remark that Hansa made about the efficiency. Of course, the greedy algorithm in the way that we stated it is very inefficient, because it would require us to store and look up this long list of previously visited permutations, which there are exponentially many possibly. And this is, of course, very inefficient. However, we can make this algorithm memoryless, so we don't need the lookup. This is just a conceptual way of phrasing the algorithm. If we implement it, we can get rid of this and make it memoryless. And then the running time is essentially determined by how fast we can check the membership in the set Fn. So how fast can we determine what a minimal jump in this set Fn is? And here we should think of this Fn not as a huge set of permutations that we are given, because if we were already given this huge set, then there would be no need to generate it. but we should think about it as given to us in terms of some properties. So think for instance, about the task is generate all permutations that have such and such property, or generate all things that forbid some pattern. Yeah, in this kind of way, we should think about this Fn. And then the question is, how fast can we compute minimal jumps with such properties? And in many cases, so for concrete zigzag families of objects, we then get polynomial time algorithms or even loopless algorithms. So loopless means constant time for each object. And in the rest of the talk, I will go through 3 examples, hopefully, of application areas of this framework. The first one will be pattern avoiding permutations. The second one will be lattice congruences, and the third application will be elimination trees. So let's see how far we get with these applications. And we have already written several things about this, and currently we are writing volume 4. So this is a somewhat extensive series of papers. So it has a lot of applications, this algorithm. So first, I want to talk about pattern avoiding permutations. So let me just recap these basic definitions. We look at 2 permutations, pi and tau, and we say that pi contains this tau as a pattern if there's a substring in pi whose entries appear in the same relative order. So for instance, here, this permutation 5, 3, 4, 2, 1, 6 contains the pattern 1, 2, 3, because these red numbers, they are increasing like 1, 2, 3. And otherwise, we say that pi avoids the pattern. So for instance, here, this decreasing permutation 6, 5, 4, 3, 2, 1 avoids the pattern 1, 2, 3, because you cannot find such a substring. And now we look at those permutations of length n that avoid each of the patterns tau 1 up to tau k, and this we call Sn of tau 1 up to tau k. So those patterns that avoid, those permutations that avoid each of the patterns. Here's another definition. A pattern is called tame if the largest symbol is not at the boundary, so not at the leftmost or rightmost position. So this pattern 1, 3, 2 is tame because 3 is in the middle, and this pattern 1, 2, 3 is not tame because 3 is at the boundary. And this is our main theorem for pattern avoiding permutations. If you prescribe any list of tame patterns, tau 1 up to tau k, then the set of permutations that avoid those is a zigzag-ling mesh. So you can use algorithm J to generate those pattern avoiding permutations. And this gives a huge family of interesting combinatorial objects, because many interesting objects are in correspondence to pattern avoiding permutations with tame patterns. So here's one example. If you avoid the pattern 2, 3, 1, you get permutations that are bijectively equivalent to many Catalan objects, such as binary trees, triangulations, and dyke paths. And then you get nice gray codes that I want to show here. So here you see the zigzag algorithm in action on these objects. On each of these objects, the minimal jump translates to these minimal changes. So you get rotation gray codes for binary trees, and on triangulations you get this flip notion, and on dyke paths you also get some notion of flips. So in all cases, you get algorithms. You get minimal change operations on the objects. So the minimal jumps translate into something nice on the objects. If you avoid 2, 3, 1, where the 2 and 3 are required to be adjacent, then you get Bell families, and you get a gray code for set partitions by exchanging elements. This is in fact exactly this gray code due to k that I mentioned in the beginning. If you avoid 2, 3, 1 and 1, 3, 2, you get peak-free permutations, and which are in correspondence to binary strings, and you recover the binary reflected gray code. Here's another family of objects. If you avoid these 2 vincular patterns, you get the so-called Baxter families of permutations, and they are in correspondence to rectangulations. Let me show you some nice pictures what a rectangulation is. So This is here a link on the combinatorial object server where we implemented these algorithms. So a rectangulation is a subdivision of a square into rectangles. And now you can generate those objects using our algorithm. And again, you get some nice minimal change operations on the object. So again, it's some kind of notion of a flip. I will not define exactly what the notion of flip is. And then you can also do pattern avoidance. Now you can avoid geometric patterns on these objects. So for instance, here, there's 8 different geometric patterns, and now you can generate all rectangulations that avoid some subset of these patterns, let's say. And in each case, you can use this algorithm and get an efficient algorithm for generating those pattern avoiding rectangulations. So let me go back to the slides. This is what I mentioned, the combinatorial object server. In addition to these classical and vincular patterns, so these were just 4 examples, but you can do many, many more. In our paper, we have like 30, 40 patterns listed. These are just a small subset. In addition to these classical and vincular patterns, you can generate pattern avoiding permutations for many, many other classes of patterns that have been studied. So this pattern avoiding community, this is a huge sub-community. They have their own conference, and they study all kinds of weird notions of pattern avoidance, and many of those we can cover with our framework. The next thing I want to talk about as a second application of our framework are these lattice congruences. So this requires a few definitions. So the starting point is the weak order on the symmetric group. So we look at all permutations. This is our ground set. And we look at the inversion set of the permutation. So we look at all pairs in the permutation where the bigger symbol appears before a smaller symbol. Where a pair of numbers appears in the wrong order. This is an inversion. Now we order the permutations by their inversion sets. So one permutation is below the other one in the poset if its inversion set is a subset of the inversion set of the other one. And then at the bottom, you have the identity permutation. And at the top, you have the reverse identity. So everything is reversed. And the rest, you get this poset. In fact, you get a lattice. So this is a lattice. And the cover relations in this poset, what are the edges in this cover graph? So going up one step in the poset means adding one inversion, so performing one adjacent transposition, putting the bigger number before the smaller number, and going down means doing the other way. So cover relations are adjacent transpositions. And this thing forms a lattice, meaning that if you pick any 2 permutations pi and rho, there's a unique smallest guy above them. This is the join, and there's a unique largest guy below them. This is the meet, and this is a lattice. And now, what is a lattice congruence? So what you do now is you have an equivalence relation. So certain permutations are considered as the same. So they are in the same equivalence class. In this picture, they are in the same blue bubbles. So these blue bubbles are equivalence classes. And these equivalence classes, they have to respect joins and meets. Then it's a lattice congruence. So what does it mean, respecting joins and meets? It means that if you pick 2 of these blue bubbles and you pick any permutation from one of them and any permutation from the other, and you compute their join, then all the joins that you get, they should be in the same blue bubble. And similarly for the meets. So this is what it means. So such a set of blue bubbles satisfying this condition, this is a lattice congruence. And there's obviously many, many ways you can do that. Many different lattice congruences. And now you can basically shrink these blue bubbles into points, and you get what is called the lattice quotient. So you get a smaller poset. So the lattice induced by the equivalence classes. So each equivalence class shrinks to a point, and you look at the induced relations. And you get many, many different lattice quotients. In fact, many interesting lattices arise as quotients of the weak order. So you start with this very special decompose it. And by doing different lattice congruences, you get different quotients, and many of them are of interest. For instance, the Tamari lattice you get in this way, or the Boolean lattice, Cambrian lattices, and many other lattices you can get in this way by choosing a particular lattice congruence. And again, there's a huge number of them. There's double exponentially many different lattice congruences. And now this is our main theorem for lattice congruences. So the claim is for any lattice congruence, we can choose a set of representatives. So from each blue bubble, we pick one permutation in such a way that this forms a zigzag language. So from each blue bubble, I pick one of these permutations from the bubbles. These are these dark blue dots. These are the representatives. So I can always choose those blue dots in such a way that the permutations I have chosen now, that they form a zigzag language, meaning that I can apply algorithm J to them. And if I run algorithm J on those representatives, this is another guarantee that the theorem gives now, then I get a Hamilton path in the cover graph of the quotient. So these changes that the algorithm J does on the representatives, they correspond to minimal changes in the quotient. Yeah, so this is some kind of guarantee of optimality. And what is this that good for? So here's one of the ramifications of this. That was a recent paper by Pilosh and Santosh where they showed how to realize the cover graphs of those quotients as polytopes. And those polytopes, they call them quotient-topes, and they generalize many known polytopes like the permutahedron, associahedron, hypercubes, and so on. So they managed to do this for every lattice congruence. They wrote down the corresponding polytope. And as a corollary of our result, we get now that all these quotient-topes have a Hamilton path on their skeleton. And this can be computed by our algorithm J. The last the last application area I want to talk about are elimination trees. Let me just check how we are doing time-wise. Okay. So for this, again, we need some definitions. So we start with a connected graph G, and an elimination tree we get is by removing vertices one by one from our graph G and drawing a rooted tree in this process. And the root vertex of this rooted tree will be the first vertex that we remove from G. This will possibly disconnect G into smaller components, and then we recurse on the connected components of G without this vertex. So here's an example. This is our graph G. On the right, I will draw the elimination tree. Let's say we first remove D. This will be the root of our tree T. And removing D from the graph will decompose it into a red component and a blue component. So therefore, this D in the tree will have two children, the red subtree and the blue subtree. And let's say I continue in the red one, so in the left component that is now left. And let's say I remove A. So this will be the next node in my tree. And now I decide to remove C, let's say, and then only B is left. So I have to put B here. And in the other component, there's only E, so I can only remove E. So this would be one way of removing vertices corresponding to one of those elimination trees. And these elimination trees, okay, so let's look at two examples. Let's look at the example where G is a path. So suppose G is a path with the vertices 1 up to n. Then the elimination trees correspond to binary trees, because if I have a path and I remove one vertex, there's always a left and the right half left, so to say, and these are the left and the right subtrees in the binary trees. So if G is a path, then elimination trees are binary trees. In particular, the number is given by the Catalan number. Let's look at another example. If G is a complete graph, then the elimination tree is a path, because whenever I remove one vertex, this G stays connected. Yeah, I keep removing vertices, but it's always a click. So that means that the elimination tree is just a path. There's never more than two children. There's always just one child. And these elimination trees that are paths, I can look at them as permutations. You know, there's just n factorial many ways of removing vertices from a click of size n. And these are permutations. And now let's look at some minimum change operation on these elimination trees. This is what we call a tree rotation. And the tree rotation on elimination trees, so suppose you have an elimination tree with an edge ij, meaning that at some point vertex I was removed from the graph, and in the next step vertex j was removed from the graph. And this tree rotation is basically looking at what happens if I swap the order of removing these two vertices. So instead of first removing I and then j, I look what happens if I first remove j and then I. And the tree that I get in this way, this is what I say is obtained by tree rotation from this tree T. So this is done here for this particular example. The subtrees of I and j remain the same, except those subtrees which in the graph lie between I and j. So some subtrees, in this case C and D, they change parent. They change their parents. And these are in the graph the ones that lie between I and j. And this, if you look at this picture, this generalizes binary tree rotations. Yeah? So in binary tree rotations, we only have two children, and then the classical binary tree rotation is exactly a special case of this very general definition here. And this is what we call the rotation of the edge ij in the elimination tree. And there's some underlying polytope for these elimination trees. So this is the so-called graph associahedron. So you can start with any graph, or in this case, connected graph. It's also possible for any graph. This graph associahedron A of G is a polytope whose vertices are the elimination trees, and the edges, they correspond to these tree rotations. Of course, this doesn't at all define the polytope, because a polytope has also faces of all kinds of other dimensions, but for the sake of this talk, we are only interested in the combinatorial structure. So you can define these polytopes in such a way that their vertices are the elimination trees and the edges are the tree rotations. This has been done by several people. And here's an example. So if G is a graph, then the polytope you get is the associahedron, because the vertices now correspond to the binary trees. So the black things that you see here, these are the elimination trees, and the blue things, these are the corresponding binary trees. And if you take the complete graph G, you get the permutahedron. Again, the black things are the elimination trees, so the paths, and the blue things are the permutations, so just writing the label of the path from top to bottom. And for every graph, for any graph G, you get another polytope. So it's a huge family of different polytopes. They are called graph associahedra. Here are some examples. If G is a path, you get the standard associahedron. If G is a complete graph, you get the permutahedron. If G is a cycle, you get the so-called cyclohedron. If G is a star, you get the stellohedron. So this generalizes many known polytopes. And in terms of Hamiltonicity, it was shown by Manuel and Pilot that for any graph with at least two edges, this graph associahedron has a Hamilton cycle. So you can walk on the skeleton, visit every vertex exactly once, and come back to the start. Their proof was existential and somewhat complicated, and doesn't give an efficient algorithm to compute this cycle. And what we looked at is how can we apply our algorithm J to generate such a Hamilton path or cycle. And we managed to do it for a somewhat restricted class of graphs G, namely caudal graphs. So let's recap what a caudal graph is. A graph G is caudal if it has no induced cycles of length at least 4. And this includes in particular trees, in particular stars and paths, and many other graphs, complete graphs, K-trees, interval graphs, split graphs, and so on. And our theorem is that if you take any caudal graph G, then we can indeed encode its elimination trees by permutations, so that those permutations form a zigzag language. Then we can run our algorithm J, and the steps performed by algorithm J, they correspond to tree rotations. So the algorithm produces a Hamilton path on the graph associahedron. So it's a constructive and efficient proof for some of the cases of this general result that there's always a Hamilton cycle. In fact, this characterizes caudality in the sense that if you run our algorithm when G is not a causal graph, then the algorithm will fail. It will run in one of these stopping conditions where it stops without generating everything. And here's this translation of the algorithm to elimination trees. So the translation of the permutation algorithm to elimination trees. Here's what you do. You start with the finding a perfect elimination ordering, which exists for any causal graph. So this is an ordering where every vertex sees where the neighbors of any vertex, any earlier neighbors of any vertex form a clique. And then you start with the identity permutation, meaning with the elimination tree where the vertices are removed in this order. So first remove 1, then remove 2, then remove 3, and so on. This is the initialization. Now comes the greedy step. So these largest jumps of the largest possible value, they translate into rotate the edge with the largest possible end vertex so that you create a new elimination tree. And that's the algorithm. And again, this is inefficient, but you can make it efficient. And if you make it efficient, you get a running time of m plus n, where m is the number of edges and n is the number of vertices of G. So this is the time it takes to do a graph search in this G. This can be improved to loopless when the graph G is a tree. And again, this what algorithm we implemented on the combinatorial object server. We have a few minutes, so let me show you this. So what you can do here, you can specify your favorite graph. Let's say we take a path on 5 vertices, and then we get all the elimination trees generated by this gray code. The trees here, they are turned sideways, so the root is on the left and they grow to the right, just to save some space. And then you get the list of all of them. So in this case, you have the path. So this is the Catalan number. This is why you get 42 here. You could also take the clique. So let me take the complete graph. Then you get permutations. Yeah, so here you get permutations because the elimination trees are paths. You get 120 of them. And you can choose your favorite graph as a causal graph to start with. Okay. So let me finish with some open questions. Of course, as I mentioned, this last result was somewhat restricted, only for causal graphs. Of course, you could ask yourself, what about general graphs? Can we also get an efficient algorithm there? Our algorithm also doesn't always give a cycle, but only a path. So you could wonder, can we always get a cycle, let's say, for causal graphs in an efficient way? This is open. The same thing you could ask for quotient topes. So for quotient topes, I mentioned that we always have a Hamilton path, and we conjecture that there's always a cycle, but we don't know if it's true, and we also don't know if we can somehow modify our algorithm to get it. More broadly, we could ask for more applications. So we've seen many applications where this algorithm works, and for sure there must be more, and there's many more things to discover, I would think. And also in terms of polytopes, there's other even more general families of polytopes that we may try to tackle with this framework. Another direction would be somehow to try and exploit this framework for random sampling. So if you remember this tree of permutations with the pruning, so this whole framework is based on some kind of generation tree. And in this generation tree, you can of course do random sampling. Yeah? You just start at the root and you go into these branches with certain probabilities. And this would be an interesting direction to explore if this gives anything new or interesting on top of generation. So this would be random sampling. That's all I wanted to say. Thanks very much for your attention, and thanks also for the questions.
Okay, thank you, Torsten. And yeah, I ask everyone to unmute themselves and give Torsten a round of virtual applause. Okay, so are there some questions to Torsten?
Torsten?
Yes.
Yeah, this is great stuff. First question, does your solution to the middle levels problem fall into this category? Lattice congruence or something?
No, it doesn't fall into this category. It's somehow too ugly to fall into this category. Like the zigzag languages are in some sense still nice. What I know is that, so for instance, Aaron Williams, I talked to him, and he's very much a fan of these greedy strategies. And he tried, with Joe Savada, he tried like tons of rules for this middle levels problem, and they all failed. Like he sat down and like tried everything natural that you can come up with, and they all failed.
Well, the other question is, can you put up, what state is your paper in? Can you put up a link to it in the chat?
I mean, the first three, they are available on the archive, like the pattern avoiding permutations, the lattice congruences, and the rectangulations is on the archive. And this last thing, the elimination trees, this is still in progress.
Okay, great. Thank you very much.
Thank you.
So this generation, I mean, it's a way how to construct a Hamiltonian path in the the flip graph or what.
Right.
So is there some easy condition that would tell you, okay, it also allows, I mean, it also guarantees me a Hamilton cycle?
Yes. There's a like the condition is like if you look in this pruned tree, and at some level n, these are where the things are that you want to generate. And the condition when you get a cycle is if you look at all the previous levels, if they all have even cardinality, then the gray code on the bottom level is always a cycle. So if all the intermediate levels have even cardinality, then algorithm J gives you a cycle. And this happens actually in interesting cases, like for instance, in permutations, it happens in the binary, in bit strings, it happens for many classes of rectangulations, like by chance. It doesn't happen, for instance, for binary trees, because the Cardinal numbers are not always even. So if you have any class of objects that has always even cardinality, then you get a cycle.
Nice. So maybe if there are no more questions to Torsten, then let's thank him again for a very nice talk.
Thanks, everyone.